Good afternoon, everyone. My name is Masako, and I am from Massey University in New Zealand. And today's topic, my topic is similar to Marta's, but in New Zealand context. And the name of the tool is called SAIDI. You probably haven't heard of, but it's famous in New Zealand. So we're exploring the integration into a real-time decision support tool for outbreak investigation in New Zealand. And this is a collaborative work with Ministry for Primary Industry in New Zealand and also a software company called Episoft. So here is my agenda. I'll talk about the biosecurity preparedness in New Zealand, and then move on to the data intelligence tool, how SAIDI was born, and then give you a use case example for a Mycoplasma bovis outbreak in 2017. And then I'll get to the point of zoning integration, so bear with me, Nicola, and then I'll end with the discussion. So this is a photo of Palmerston North, where Massey University campus is located in. So it has some beautiful river, rainbow, but you might notice how empty it is. So we are a country with only 5 million people, but we have 10 million cattle and 24 million sheep. And the country is heavily relying on the export of livestock products. And so we are small humans, and there are only 3,000 registered vets in the whole country. And vet epi, we don't have the number, but we are even rarer and a niche species. And the question is, are we prepared for animal disease incursion? This is a constant concern for us because we have a large susceptible animal population, but a small vet epi community. The strongest defense is the border biosecurity. We have a very efficient X-ray in dogs. So if you forget to declare an apple, then you will suddenly turn into a criminal. Be careful. But we still occasionally have a disease incursion. And we tend to repeat infinite loop of response, biosecurity response, panic, and then forget. So our epi group, the senior epi group, have come up with the idea of developing a generic intelligence tool that is reusable and that works on real-time, web-based, and accommodate centralized database and have generic report templates. And that is called SAIDI, Standard Analysis of Disease Investigation. So this just shows a simple history of how SAIDI was born. So New Zealand is very scared of FMD. So the epidemic in the UK really was a big shock to New Zealand. And also we had a hoax. Anonymous letter came from Palmerston North, and it says that they released the virus in an island. So the government had to spend a lot of time for investigation. And that is about the time when SAIDI was developed, the initial version was developed, and it has grown with the biosecurity threat. So as mentioned, in 2017, New Zealand first detected the Mycoplasma bovis, and the decision was to eradicate the disease. And New Zealand wants to be the world's first country to eradicate this disease in 10 years. Let's see. And so the SAIDI was used during this time, and it evolved into the current form. And also now the country is worried about avian flu. It had an incursion in the last December, but luckily we only had one farm infected, and it managed to contain it, so we didn't really end up using SEIDI. So this is the structure of SEIDI, briefly. So the data is collected from the field, and it's cleaned and formatted and goes into the central relational database. And this is connected with the R environment. So it's kind of like Microsoft Access and RShiny combined, but it's owned by the government server, so the security issue is cleared. And then the data import and also the generation of reports can be automated, and it can reflect the most recent data. And this is the 3 core data of SEIDI: outbreak data, tracing data, and the population data. And they are all connected using the unique farm identifier as a common field. So outbreak data is collected from the surveillance and the diagnostic teams. They enter the data, and when test results come positive, then that will go into the outbreak data. And we also have national movement data called NATE. This is not mandatory, so there are still some gaps, but it's still better than nothing. And the population data, we have a data called AgriBase, and that's commercially available, and it stores the location of all farms in New Zealand with the number of animals, and this data is updated regularly as a routine biosecurity. So with this, SEIDI can work magically using the R scripts that's been developed prior to this. So there are about 30 R reports, and it can generate basic epidemic curve, descriptive spatial temporal analysis, or network analysis, or those charts to check the efficiency of response activities. And it keeps developing. Where there is need, we develop the report templates, and it can be scheduled to update regularly every day or every hour. And SEIDI also has mapping functionalities. It's interactive, and the mapping layer is overlaid on the OpenStreetMap or satellite image. We can zoom in or out and display attributes like farm attributes or the risk event attributes. And because we create this map layer using R, we can incorporate some algorithms. For example, that is showing the predicted source farm or destination farm based on the distance from the infection farm, and that might be useful for surveillance activities. So as said, during the Mycoplasma bovis outbreak, we decided to use SEIDI for the response. And because SEIDI was initially developed for FMD, there was some modification to make. So the biggest difference is that M. bovis spreads much slower than FMD. And also it takes months until the confirmation of the infected farms, which means tracing can involve like dozens of movements, risk events, and farms. So this plot shows the timeline of tracing events that happened from the estimated infection date until the confirmation. And there are just so many movements that happened during the time when the farm was infected but not detected. And I remember early on I visited MPI and saw floors full of people manually working on producing these timelines using Excel. And of course, it's tedious, it takes time, and it's error-prone. And once we made this algorithm in R and automated, they were so happy to not having to do this manually, and it freed this staff time so they can spend their time on something more useful, other things. And also it improves timeliness, consistency, and accuracy. So we also developed some maps for Bovis outbreaks. There were about 200 infected farms that we identified back in 2018-19. And as you can see, it just spreads everywhere. It started from the South Island, but it was found to move up north and down south. And they were all connected with the movement. And these show the farm attributes, how many animals there are, and the date of infection or response activities or tracing activities. So we didn't end up using zones because Mycoplasma bovis is not that contagious. The local spread is not so important. And also because the infected farms have spread all over the country, so we didn't use zoning. But SAIDI is a living tool. It can be modified and refined where there is a need. So after the inquiry from Nicola's team about integration of zoning, we have had a thought. And well, my quick thought is why not? Because it's technically not too difficult to do that. We just have to code it in R. So it would be like first to identify the infected farms, and then we make a criteria of infected zone, protection zone, containment zone, or free zone, and then generate the output in the GEOZONE format. And we already partially have the code to do that, and I think it's just a matter of some time to do that. But it's not really, the problem is not up to me. I have to talk to my collaborators in MPI. I think, though, it's a good timing to do so because the country is now worried about avian flu, and they would do anything to minimize the risk of, minimize the trade impacts or make it easier to control or communicate better. So I think we will have some discussion if this is the next things to implement in SAIDI or not. So as a discussion point, SAIDI is a real-time intelligence tool that can synthesize and analyze data during an epidemic response. And it was proved to be useful during the Mycoplasma bovis outbreak because it can shift the staff focus from the manual labor, the number crunching, to optimal data collection, assessing data limitation, or interpretation. So the possible future work, I put GEOZONE in the first point. Also, training staff to use it. It's user-friendly and it's not that hard, but still they need to learn how to use it. and we will try to make the reports more more intuitive. And also identify any further tasks and incorporate them into SEIDI, or linking with simulation models, infection disease spread models. That's our next goals. And we have a paper published in Frontiers in Vet Science if you are interested. And I acknowledge MPI for the funding and all these people who have contributed to SEIDI. And I will end with another picture from Palmerston North. Thank you. Any questions?
Yeah. Question for Masako. Okay. You said that you made an attempt to incorporate the GEOZONE. You said that it seems easy, no, our application. So technologically speaking, introduce the idea of zoning management in a tool like the one that you presented, that is more oriented in the disease support, disease response support. Do you think the organizational part of working with Zone, so the CVOs, the local health units, and also the trade ministry that should be involved in at least the free zones, or in all the activity related about Zone as a tool. How much this can impact in the implementation of a protocol linked with the zoning tool, according with your opinion?
I think having like a one consistent system to produce zoning, it really makes it less confusing and consistent. So I think it's really good. New Zealand doesn't really have any free zones for any diseases, so we never really had any situations like that. So I can't really imagine how useful it will be. But I think eventually just having it developed and being ready makes a big difference. And also, I remember we talked about dynamicity, addressing dynamicity. So that's another thing that having this kind of tool linked with data would perform well, because we created a zone and the next day there may be a new infection, but if this process is automated, then it's easy to update the zone outputs, and yeah, that may be good.
First the lady, and then, first the lady.
Thank you. Are there any diseases that cannot be traced, controlled? You cannot use this tool for any disease. You mentioned yesterday leptospirosis or another disease. You have a lot of problem in cattle. So do you use this tool for that, or?
Yes, good point. So we just think using this tool for an epidemic, a new incursion, but I don't think it works well for endemic disease, because it's everywhere, and I don't know if there is a need for that when there's no response triggered by detection of this disease.
The study it's also included also the opportunity to manage fish diseases, or fish outbreak, or fish events, or is just only for terrestrial diseases?
At the moment, we only have the population of land animals. We don't have fish farms incorporated in there. So that would be the first step if we want to include fish in there.